Ever pushed a syringe filled with air? If you've tried this before, you'd know that it pushes well initially but eventually hits a point where it won't budge. This is because the increasingly compressed air fills the narrowing space within the syringe. What about light, then? Will light compress like air, refusing to move? Or will it be pushed without resistance till the end? Recently, scientists conducted experiments to compress photons to answer this. And they discovered a very surprising property of photons. Humanity has compressed a great variety of materials up until now. But there are few instances of recording the process and force required to compress light. Perhaps due to the nature and purposes of light, there was hardly any need to compress it. So, scientists decided to find out if light could indeed be compressed through experiments. For this, they prepared a special tube fitted with 2 small mirrors. They then trapped a certain amount of photons between the 2 mirrors. In this state, they moved one of the mirrors to attempt compressing the photons. But just like before, the mirror, initially moving with little force, hit a point where it wouldn't budge. In fact, this result was something the scientists had fully anticipated. Though photons generally don't have mass, they do possess kinetic energy. The photons were constantly bouncing between the 2 mirrors, generating kinetic energy. But as the space between the mirrors narrowed, the bouncing of the photons became even more intense. This increased kinetic energy of the photons acted as a resistance against the force pushing the mirror. As the number of photons increased, so did the force required to move the mirror. Nonetheless, the scientists continued to exert greater force to push the mirror and compress the photons. Then suddenly, a peculiar phenomenon began to occur. The force needed to move the mirror weakened abruptly, and eventually, it could be easily pushed with little to no force. What exactly was happening with the compressed photons? In fact, the answer lies in the realm of quantum mechanics. In quantum mechanics, photons possess not only particle-like properties but also wave-like properties. Hence, the position of a photon is not precisely determined but rather vague and probabilistic. Unlike other particles, photons do not experience electrical repulsion even when they are in close proximity. When the photon density exceeds a threshold, their probabilities of existence overlap, leading them to behave as a single entity. As these overlapping photons move like waves, it becomes increasingly challenging to distinguish them from one another. The weakening force to move the mirror was due to the photon overlap phenomenon. This unique phenomenon is exclusive to photons and cannot be observed in other particles. By effectively utilizing these characteristics of photons, it is possible to develop highly sensitive devices. For instance, it is possible to create highly sensitive sensors for measuring forces such as weight. Photon pressure-based sensors can be incredibly sensitive and precise, surpassing other types of sensors. Moreover, light may possess even more astonishing abilities than we can imagine.